Okay, so hi. This is Ethan and I's project on calibration for reinforcement learning. So I'm going to start by just kind of giving an overview of the problem we were tackling and what we did in terms of reviewing past work. And then I think Ethan will handle the second half of the presentation going over methodology and results. So in terms of the problem we were tackling, we were kind of focused on model-based reinforcement learning. Um, so that's the setting where essentially we have a state space and an action space. And we are trying to learn a policy where at every sort of state, we have an action or distribution over actions. And the goal is ultimately to maximize an expected reward with a reward coming at every time step. And there's sort of more technical details like a discounting parameter over future rewards, but that's kind of the setting. And the part of this setting that's interesting is that we kind of assume in the model-based RL model that there is a ground truth transition function, which looks at the current state and the action we play and then gives a distribution over future states. But while we assume that the ground truth exists, we don't actually know this transition function. So most model-based RL frameworks try and learn a transition function, which is also sometimes called a dynamics model, and then use that to estimate expected reward, and then maximize the policy based on that expected reward. And so we're interested in making these transition functions better. Sort of not rigorous but motivating example was the lecture that we had on calibration being useful for downstream agents, and that got us thinking about sort of the RL case where we're learning policies. And so we're interested in making transition models better, and in particular, we're interested in making them better through calibration, ideally as a sort of post-processing step. Um, and we hope sort of that by calibrating these models, we can get better performance on our cumulative reward kind of downstream. And so we verify that empirically, but also we review a few relevant papers from RL about this. So now I kind of talk about the structure of our paper. So we start with an introduction, and then in our background section, we sort of more formally lay out this model-based RL stuff and kind of talk about the goals of that model. Then we review calibration sort of in the context of the class, and sort of why calibration is good or desirable, particularly in the RL context. Um, and then we start talking about what it means for a transition model to be calibrated. Sort of the part that was tricky for us is that we learned a lot in class about sort of calibrating a single model and getting guarantees conditional on that model's predictions. But the object we're trying to calibrate in a sense for these transition models is we don't want to calibrate a single sort of probability distribution or like a single sort of model that outputs a number, but rather we're trying to calibrate the transition function so that every output probability distribution is calibrated. So to first of all understand what that means and then to look at approaches, we really relied on these two papers. So this paper from Kuleshov in 2018, and then this paper also including him and others in 2019. So this paper, which we review in the project, defines calibrated regression and defines calibration in the context of CDFs, which is the type of calibration that we hope to achieve or that we try and achieve. And then it talks about an algorithm for actually achieving this, where in particular, what we really focus on is this part of their algorithm, which talks about how to construct recalibration data sets. And we talk about it sort of more in detail in the paper, but the goal there is to have our output quantiles match the true quantiles, and then we estimate quantiles empirically, sort of averaging over the observed transitions that we have in our data over all the time steps. And so this paper is kind of written in the distributional setting where we see a value X, and then based on X, we output a forecast over the value Y. And then we do that over time. So it talks about calibrating sort of all of these distributions sort of conditional on our input X, but it doesn't really talk about the RL case. And that's where we sort of draw on this paper, which applies the methods from the previous paper to transition models in reinforcement learning. So this is really the paper that kind of inspired us. And in particular, we kind of review this paper and we look at some of the environments that they're calibrating in, but we just pick a different sort of final post-processing recalibration function. Um, so in particular, I guess the formulation we arrive at, which is based on that paper I was just showing, is uh, excuse me. Oh yes, so is essentially taking our base transition model and then fitting a ideally cheap to compute regression model that'll kind of like fix the quantiles. I guess this is analogous to the value patches we were doing in the simpler case in class. And we talk about the different models that are available. The model that this paper I was just referencing uses is Platt scaling and extends it to the continuous case. We use a different model for this particular use case. We use isotonic regression, which is a bit more powerful and non-parametric, but has its trade-offs, and we get some pretty good results that Ethan will talk about. And then the final part of sort of the review, which unfortunately we didn't get great results for, but we just wanted to touch on, was this paper that we found where they defined something that they called a GP beta method. So this is another attempt at doing post-processing calibration on output distributions, but in particular where the output distributions are normal, so just defined by a mean and a variance, and it uses a Gaussian process like approach to essentially learn things about these distributions, even though all of them might be unique. Over time, we might produce output distributions that are similar, and so it measures that similarity using kernel-based methods and sort of encodes that. So we reviewed this paper briefly, but we didn't get great results from it. So that's kind of something we leave as for the future. But yeah, that's an overview of the sort of review we do in the paper. And then I can pass it over to Ethan for what our methods and result look like.
Yeah. So as Ron like briefly mentioned, we decided to basically try our like hand at an environment that they tested on also the like specifically in inventory management. And more and to get into details, I guess. Basically we took an online data set from I believe an Ecuadorian grocery chain where they kind of mapped for each day and for each item and for each store I guess the number of units bought. And then from this similar to the matter described in one of the papers that we looked over, we kind of computed rolling averages of unit sales as well as periodic features and day and week features for day of week to kind of compute a broad state space, right? So the periodic and day of week features kind of encode I guess the day part of the state space, and then the rolling average features kind of encode the like the past seen demand, and is obviously will be helpful for the transition model to like predict the the demand on that particular day. And note that for this problem we're kind of making the abstraction that demand for a day is kind of analogous to the number of sales that they'll actually get up to like some noise, of course. Our action space then correspond to ordering decisions, and for the purposes of this implementation, if the transition model thinks that there's going to be X amount of units sold for this item, it's going to believe that it needs to order like up to that amount to kind of fulfill that order, right? And then we just a few definitions. Stock out is kind of like the difference between um, the demand and how much of that item we have for that day. And then the waste is the opposite of that, right? So if there's demand for 50 items and we only have 30, that means that we don't have enough items and therefore we stocked out people. And the reverse of that, in that, oh, let's say there's demand for 30 and we have 50 already, then we're wasting 20 items kind of. And yeah, and so on to like the transition model itself, we just use like a very simple like 5-layer MLP. I guess the interesting part, kind of to like approximate and to have the model like output probability distributions for every single input. We train it with dropout, and also at inference time, we also keep the dropout. And essentially, we sample this model, I think for 300 times, to get like different values, and from that approximate like a probability distribution for each input. And to clarify, I forgot to mention this, but this data set is huge. So we took the top 100 stores by sales, by number of sales, and then took the top 100 items for those 100 stores to like clean our data set. And essentially, for each item, each of the 100 items, we train a separate transition model that predicts, for the given time features in a given past unit sales feature will predict like the sales for that particular day. So that's kind of the setup we have. Um, and for plannings, we have two kind of planning sort of policies. One's just like a basic heuristic planning where the model will query the transition model for how much demand the transition model thinks we'll get for that day, and then it'll just multiply that by 1.5 and be like, oh, that's like how much of the item will actually happen for that day. And that's just kind of a heuristic that we want to order for every day 1.5 times like the expected demand. And then a more sort of, you know, encompassing approach is MPC, where we basically simulate rollouts. In our case, we simulate 20 rollouts over a horizon of 5 and just kind of select the action that gives us the highest reward over those 20 rollouts. And yeah, and then onto the calibration part. Uh, we train in a method described in the paper, like kind of like two calibration models, one for isotonic regression, one with GP beta regression. Yeah, for details, you can look in the code and quick look at the results. Basically, isotonic regression, did improve markedly the reward. GP beta not so much. And it turns out that we suspect this might have happened because of the underlying assumption that GP beta has, which is that the original probability distribution that you give to it is already normal. And as you can see from here, that it's not often that's not often the case. This is obviously like really really right skewed. The screenshot in the paper is like for a particular item for a particular day, but as I like go through like more and more draws from the trans model for like a different item for a different day, you can see that this is generally the case. It is right skewed. Um, and yeah, but yeah, that's our paper. The code I believe is on GitHub. There's a link I think in the paper, but yeah, that's our project.
Cool.
Cool. All right. Thanks.